Hello everyone, my name is Alejandro Reyes. I'm a first year PhD student in Assistive Technologies at Laval University. In this presentation, I will talk to you about a tool that we have developed for its use in virtual environments, which is intended to allow the user to know their own information on 3 different physiological markers, and this from a biofeedback perspective. That means that it aims to make the user aware of their physiological, emotional, and cognitive states in order to be able to regulate themselves. This tool was developed as part of a research project we are carrying out at the Interdisciplinary Center for Research in Rehabilitation and Social Integration in Quebec City. This project aims to promote employability of people in handicap situations. The problematic that we are trying to address here is that there is a large number of people in handicap situations who, even after having obtained their high school diploma, are interested in getting a job but they do not succeed. Among many reasons are prejudice, inaccessibility, or lack of adaptation of workplaces. Among this type of population, we find autistic people who might give up even in the first stages of training for a job. For this, before the health crisis started in 2020, there were support tools such as the Workplace Learning Program, which in its original version aims to pair a more experienced worker, who is usually called a coach or a companion, with a more inexperienced one. There are versions of this companionship program that have been adapted in various organizations to be able to accompany people in a motor, sensory, or intellectual handicap situation so that they can integrate into a company and finally land a job. Then, as I mentioned, the health crisis set in, leading to the closure of the educational and professional insertion platforms in person. In this context, we are exploring then the use of virtual reality technologies to remotely develop social professional skills, and this way to promote the employability of people in handicap situations. More specifically, autistic people who have obtained at least a high school diploma. And therefore, within the experimental framework of this research project, we develop a virtual reality environment that simulates a real working environment. It aims to allow autistic people, by using a head-mounted display and having access to an internet connection, to synchronously and remotely experience what the first stages of training and integration in a new job would be like. In other words, people in handicap situations such as autists could use this device, which we have called virtual companionship, to familiarize themselves with the way of life, the facilities, and even train for a task relevant to the job, without the need to travel to the workplace, while interacting in real time with a company representative who guides and trains them. Some of the elements that make up the simulation focus on being able to reproduce a series of activities that would allow the user to reinforce the sentiment of a routine and familiarize themselves with the company before going on site. We have included, for example, panoramic pictures of the real site, which can be accessed without leaving the main VR application and which allow the user to get to know the real facilities. We have also added the gameplay component, which makes the simulation similar to a video game where there are stages to follow. We also added a modulator panel, which makes it possible to adjust certain environmental parameters of the virtual environment according to the user's sensory needs, that is, to adjust the sound and light levels, and there's also the possibility of adding NPCs to allow the user to progressively adapt to the presence of others in the scene. We have also added a small panel that allows to provide information about 3 different physiological markers, which we will talk about today. Before we get into the biometric panel, I would like to show you a little insight into this application. This is a video that briefly explains the virtual interface. It lasts a couple of minutes, and there's also a showcase that is set up at this event presented by my colleague Dominique Michaud, also from Laval University, that shows in more detail the use of this virtual environment. If you assist, you will be able to wear the head-mounted display and perform a little demo. And this demonstration will be on site on the 30th of March in room 2 from 10:45. So what are we looking now at is the setup of our experiments. We have on the left side at the top the person that we call the companion, who is wearing the virtual reality helmet and who guides the student within the virtual environment. Next to them is the research assistant. On the right side we have the autistic participant, who also wears an HMD, but is in another room simulating the context of isolation and remote learning that characterized the health crisis of 2020. We have collaborated with a company in the region who allowed us to make scans so that we could reproduce in virtual reality their facilities, allowing the simulation to be as accurate as possible. So both the participant and their companion interact within the virtual environment through avatars, and there is also the possibility of direct voice communication. So this is a tool that aims to familiarize themselves with the company and to reinforce certain practices related to the routine in the workplace. We know that establishing and practicing a routine is important for autistic people, as it can create a certain sense of order in their environment. Another component of the virtual environment is that it simulates a game where there are stages to follow and objects to collect, for example. So there is the real-time biometrics panel, which we will go into more detail in this presentation. Also, as we have mentioned, there's a panel that allows to adjust the environment according to the sensory needs of the user. For example, the lighting levels inside and outside the facility, the volume of the ambient sounds, or the number of NPCs in the environment that can also be adjusted using this panel. It is also possible to consult a list of to-do activities to be carried out within the simulation at any time. And as I mentioned previously, we have also integrated some sort of capsules that allow to access panoramic photos of the real facilities. About 15 panoramic photos can be found in different areas of the virtual facilities, such as production areas, the main corridors, dressing room area, and this again with the objective of allowing familiarize themselves with the place before going on site. An also important component of the simulation is the reproduction of a task relevant to the intended job. It should be noted that as this is a demonstration simulation, our efforts were rather focused on reproducing a task in a simplified way. That means that no advanced knowledge related to the job is required to perform the task in the virtual environment. And finally, although this application is intended to develop certain social professional skills, in the workplace, we must emphasize also that the interactions between the companion and the student are not only limited to a technical or professional level, but rather we want the people in handicap situation to feel welcome, and this way promote their integration and employability. So this was a video presentation of our virtual environment. One of the components included in the virtual environment is a dashboard or panel of physiological measures, which is based on the principle of biofeedback, which by definition consists of using instruments to reflect physiological processes of which an individual is not normally aware of, so that they can control these processes voluntarily. The examples that exist in the literature of the use of biofeedback with autistic people are intended to counteract social markers characterized as typical of autism. However, the expected utility of our tool is rather to provide a useful tool to the person who is integrating into a work environment to be able to self-regulate. That is, to make it easier for them and their companion to identify uncomfortable or stressful situations and a way to solve them. It is also worth mentioning that this tool would not be classified as affective computing either, since there is no automatic reaction or adaptation of the environment based on the information collected by the biometric sensors. As far as its design is concerned, we have decided for a somewhat minimalist design. Its composition is rather a set of 3 bars showing the level of 3 different physiological measurements. The panel is displayed on the right wrist of the virtual avatar. The design is very uninvasive. It can be consulted at any time and also can be hidden when desired, although its dimensions make it hard to divert the attention of the user. On the panel itself, there are 3 icons representing each of the physiological measurements, which we will describe next, and it is rather the companion who explains in a very simplified way what each biometric signal refers to the user. There are 3 biometric signals that we have included here: the level of mental workload, the first icon and the first bar from top to bottom, the level of relaxation, icon and bars in the middle, and the physiological measure of RSA or respiratory sinus arrhythmia, which refers to the bottom bar. Moving on more technical aspects of our approach, there exist several examples of biometric panels for research applications, but There are not many examples that allow to broadcast biometrics in real time within a virtual environment. And to achieve displaying these signals, we have actually used a fairly simple approach. The treatment flow starts with the wearable broadcasting the signals by Wi-Fi or Bluetooth protocol. Then by means of a script we receive this data, and in the case as we will see of the RSA metric, we apply some pre-treatment stages of filtering, processing and calculation of the metric. This would allow us to create a CSV file where only the last values received or calculated are saved, and finally from the engine side, another script is responsible for reading the CSV file and translating it to the level bar format we've seen. The first two bars show the level of attention and the level of relaxation respectively. As we will see next, both metrics are collected by the same wearable sensor and are calculated by the manufacturer's own algorithm. The level of attention, as the manufacturer calls it, indicates the intensity of concentration or mental focus. This level is suggested to increase when the user focuses on their attention on a single thought or on an external object, and decreases when they are distracted, when they have wandering thoughts, and even if anxiety is present. The meditation metric, which is the second one, is designed to indicate a user's level of mental calmness or relaxation, and is related to reduced activity of active mental processes in the brain, such as when we close our eyes. The developer suggests that distractions, wandering thoughts, anxiety, agitation, and sensory stimuli can reduce values on the meditation meter. We decided to include both metrics as attention abilities are critical skills for learning and appropriate social development. We aim to identify attention problems that may interfere with their cognitive efficacy and socialization while on the simulation. The wearable we have used is a MindWave Mobile 2, which has several advantages, such as its low weight, less than 100 grams, its non-invasive design, its wireless connectivity. It communicates via Bluetooth protocol, and it is worth mentioning that it has been widely used in the literature in studies of psychology, affective computing, and in brain-machine interface applications. The wearable is made of an EEG system with a single electrode positioned in the FP1 position of the 2020 system, and as we have mentioned, it is the developers of these two who have designed the algorithms for interpreting the brainwaves, which are probably alpha and beta wave amplitudes for the level of attention and delta and theta wave amplitudes for the level of meditation. Which is also remarkable is that it is very well suited for use with a head-mounted display. As it can be seen in the image, we were able to position it on top of the straps of the MetaQuest 2. The clip to be placed on the earlobe did not interfere with any other component of the head-mounted display, and the electrode is placed next to the visor here in the central part of the user's forehead. Now we move on to the RSA measure. We are proposing here monitoring the RSA metric, which stands for respiratory sinus arrhythmia. The respiratory sinus arrhythmia, by definition, is the variability of the cardiac pulse in synchrony with breathing cycles. That means that the times between two successive R waves, which are these peaks that we can find on an EKG signal, is shortened during inspiration and extended during expiration. This is a phenomenon that reflects breathing and circulatory interactions, which are also observed among other vertebrates, and it has been suggested as a metric that provides insight into different neurophysiological mechanisms that may contribute to behavioral challenges in autistic people. More specifically, it is described in the polyvagal theory that the vagus nerve controls the heart by regulating the sinoatrial node, which is also known as the heart's natural pacemaker. This way the RSA is a quantification of the control of the vagal nerve. More specifically, it is described in the polyvagal theory that the vagus nerve controls the heart by regulating the sinoatrial node, also known as the heart's natural pacemaker. Therefore, the RSA is a quantification of the control of the myelinated vagal that has over the heart by measuring heart rate fluctuations during continuous breathing cycles. It is also described in the polyvagal theory that to promote effective social communication, the myelinated vagus actively inhibits the heart rate, which means that higher RSA reflects greater myelinated vagal control of the heart, which also would suggest a calm, autonomic state that is theorized to promote social communication. On the contrary, a lower RSA indicates reduced myelinated vagal control that may enhance defensive behaviors, such as fight-or-flight response, and that might interfere with the ability to regulate the behavioral state for a spontaneous social engagement. As such, RSA provides a non-invasive index of a neurophysiological state that is related to social behavior in autistic population, which is something that we wanted to display on the RSA panel bar. The lower RSA values on the panel means that uncomfort followed by defensive behaviors may occur, and the higher values, the more efforts are being done to engage socially and with the environment. For its estimation, we start from a PPG signal collected with an emotive sensor, which allows several biometric data to be collected simultaneously and remotely. And while the most conventional methods to obtain the RSA include the use of an EKG and a respiratory cycle sensor, usually placed on the chest, it is possible also to extract components derived from the variability of the cardiac pulse using the PPG signal. That means that although PPG does not replace the EKG, PPG also provides information on cardiac pulse variability, and it's precisely in its high frequency component, which ranges from 0.15 to 0.4 Hz, that data on several parasympathetic processes related to the respiratory cycles can be obtained. Afterwards, once the variability signal has been decomposed, the most common method according to the literature is to calculate the natural logarithm of the high frequency amplitudes of this variability. This way we can obtain an RSA index which is even broadcasted to the panel bar, as we have mentioned before. And additionally, we have added a small static indicator in the form of green line indicating the range of the index values considered as a baseline. In this example is from 5 to 8. And then, at the extremes of this range, that is that high RSA could then reflect efforts to engage socially with an environment, while low RSA could denote fight-flight reactions. The type of results we can present regarding the evaluation of this tool are rather preliminary and qualitative. That means that although this component is not the only one we have evaluated during the experimental stage of this project, in our methodology we have included some questions within our measurement tools to evaluate the perceived usefulness of this biometrics panel. At this moment we are in the analysis stage of this data, but we can say that we have also obtained the user's opinion regarding this tool. We have recruited autistic people who have obtained their high school diploma and who were interested in entering the labor market, so that they could test our VR system. And some of the comments that we have been given are along the lines of I feel that these measures could reflect my actual physiological state, which could denote that it could be a useful tool to monitor oneself and become aware of one's physiological state within a virtual environment. Conversely, it was also mentioned to us that it would be useful to add reminders such as some kind of alarms, as the user often did not remember that this tool was available to them. So we could add reminders every few minutes. We also believed it would be more interesting to send alerts every time the values of these biometric markers are out of range that we would establish as ideal. Finally, we would also like to add the possibility to automatically adapt the environment according to the physiological demands of the user. That means that at the moment it is possible, for example, to adjust the number of NPCs in the scene, to be able to adapt progressively to the amount of people that could be present on site. But it could also be interesting to adjust certain parameters of the environment to make them more suiting when the level of relaxation is low, for example. So this is all the material I have to present it to you. I hope you find this presentation interesting. If you have any questions, please do not hesitate to contact me or one of the corresponding authors by email. Thank you.